This video is going to talk a little bit about pressure as it relates to fluids. To begin with, pressure. It's P is equal to force F over A, that's capital P, and that P stands for pressure. Pressure is equal to force over area. So in terms of SI units, that's a Newton per meter squared. However, we want to honor another physicist and mathematician. His name is Blaise Pascal. So this is kind of what he looks like. This is my Wikipedia image. So here's Blaise Pascal, and to honor him, we name the unit of pressure after him. So we call it pascals, not newtons per meter squared, but pascals. Force, of course, measured in newtons, and area is measured in meters squared. So pressure is force over area, but it's really good to think about pressure in terms of force times area. Just rearranging the math a little bit. So as an example, conceptually, if we look at this, I've got a dragster and I've got two parachutes, the red chute and the blue chute, red one being bigger. So the red one's going to feel a large force because it's going to have a large area. Now the blue one, if it has the same pressure on it, it's going to feel a smaller force because it has a smaller area. So it's just a proportionality, directly proportional, easy to look at. So the larger parachute has a greater stopping force just because it's greater area, assuming the pressures are the same when we compare the two. Now let's look at pressures that oppose each other and tie it into something we've studied before. So Newton's first and second law says basically, when forces balance, you get a constant velocity. When they're unbalanced, you get a net acceleration. For fluids, we express it in terms of pressures. So when the pressure is balanced, you get a constant velocity. When they're unbalanced, you get a net acceleration. For example, is this balanced or unbalanced? So that happened kind of fast, but here's what it looked like every second of the motion. So does this look like it's moving at a constant velocity or accelerating? Well, to me, it looks like it's accelerating to the right because the space is getting bigger every second, the space apart each box. So therefore, the pressure on the left side of the box is bigger than the pressure on the right side of the box, so it accelerates in that direction. Balanced or unbalanced? So now let's look at it every second of the motion. So I can see the distance between the boxes is equally spaced, so the pressures are the same. It's balanced. It's a constant velocity. All right? Let's go for this again and try one more. Balanced or unbalanced? Okay, it's done. Well, it's balanced because it's moving at a constant velocity. In other words, it's a constant velocity of 0. Kind of boring, but constant velocity of 0. So now let's look at pressure's other cool properties. So here I've got basically a sphere or a bubble. And if I look at this, the pressure always acts perpendicular to the surface. Even though it's curved, pressure acts perpendicular to the surface. Unlike forces which have a direction, our pressure can be perpendicular to the surface. Now let's look at it and look at balanced pressures. So on the outside of a bubble, I've got atmospheric pressure, and if the bubble's not growing or shrinking, in other words, it's not accelerating in one of those two directions, then the atmospheric pressure is balanced by the pressure inside, which is also atmospheric. Now, I'm neglecting the fact there is some elasticity in the bubble, so we'll just keep it kind of simple here in Dr. Seuss physics. Alright, unlike forces that act in one direction, pressures act in all directions. So here's a diver underwater, and when he feels pressure, well, he doesn't accelerate up or down or left or right. He just hovers there, and the pressure that he feels is the same. If it wasn't, he would accelerate in one direction or another. Another cool thing about pressure, because it acts in all directions, it's pushing the water molecules in all directions, that if I compare the pressure of the diver to the pressure of the top of the little ravine, let's say location A, and it's the same depth below the surface, it doesn't matter that A is in this little cavity over here on the left-hand side. The pressure on the top of the surface at that same depth as the diver is the same pressure. That's because pressure acts in all directions, so at the opening of the opening, it's pushing sideways very strongly. In all directions. That's the key thing about pressure. It pushes the same in all directions. Okay, so here's a little question. Why wouldn't you choose high heels to walk in the snow? And the answer? Well, your weight is the force down, and by using a small-soled boot, the pressure will be high, and the boot will sneak in the snow. That's because pressure is force over area, or in this case, weight over area, because that's the force. And the area is really small. So heels like this, they can do a lot of damage. How would you change the boot so you don't sink in the snow? Well, let's think about this. Pressure is weight over area. So what I can do is if I increase the area in terms of a fraction, that'll make pressure smaller. So we need to increase the area of the sole. So to do that, well, basically I'll make it a snowshoe. Looks kind of funky. So that's what a real snowshoe looks like. But that's the idea behind them. And there are animals out there that have this for their feet. nice big natural snowshoes.